All right, folks, these are the solutions to the worksheet on projectile demos. Okay, so question A is find the horizontal and vertical velocities of Julian's bullets, t-shirts, let's say. So Julian's t-shirt is going a little bit over and a little bit up. Okay, and remember the goofy mnemonic is this is 8 cosine of theta, which is, sorry, you have to use trig to find theta. Um, the theta is 36.32. I will tell you what theta is on the test, so just pretend like I labeled this theta 36.32. So it is 6.45, but that is going left. So the initial horizontal velocity of Julian's t-shirt is minus 6.45 meters per second. And then his vertical velocity is 8 sine of 36.32, which is 4.74. And that's positive because it's going up. All right, and then this is Emma. This is actually Miss Levinson's daughter. So Emma's t-shirt is headed over at 5.5 cosine of 36.32, which is 4.43 meters per second. And her t-shirt is headed downwards at 5.5 sine of 36.32. But it's negative because it's going down, so that's minus 3.26 meters per second. Okay, let's go. And then again, you can get out your aggressions for whatever it is that is upsetting you today and cross those numbers out. Okay, so Emma's Vx is positive because it's heading to the right. And the Vy is negative because it's headed down at minus 3.26 meters per second. Okay, check. That is A and B. Write a position function for the horizontal position for Emma. So Emma, remember when we did collisions, we need a subscript because there's two different things happening here. So x of Emma equals x naught plus v naught t plus at squared over 2, but there's no forces left and right, so it is 0 because she does not have a head start. Horizontally, she is at the origin. She has and so that is 0 plus her horizontal speed, so 4.43 t. Okay, done. Write a position function for Julian's bullet. So x of Julian is x naught plus vt, because he also has no acceleration. He doesn't start at the origin. If you define this as the location 0, 0, she doesn't, she is on the origin horizontally, but he is at 9.25. So he starts at 9.25 meters, and his t-shirt is headed backwards at 6.45 meters per second t. That's what we found. That's what we found that first. Okay, so that's x Emma, x Julian. Write a position function for Emma's bullet for in the vertical. So y equals y naught plus v naught t plus at squared over 2. She is on top of the cliff. So She starts out at 6.8 meters, headed down at 3.26 meters per second t, and then gravity is pulling it down even faster and faster and faster. Okay, so she's got a complicated vertical. She has every single term. And Julian's bullet is, oops, Emma. Julian. He starts on the ground. His t-shirt is headed upwards at 4.74, and gravity's pulling it down at the same rate. So that is Julian. So, review question, collision. Find the time that they collide by setting the horizontal position functions equal to each other. All right, so let's try that. So remember, to show your work, x of Emma equals x of Julian. So I think I flipped them on the key. X of Emma is 4.43 t. Let's just check that again, I think on my handwritten key. Yeah, so x of Emma is 4.43 t equals Julian started out to the right of the origin, headed backwards at 6.45 t. So let's add 6.45 t to both sides. And that yields 10.88 t equals 9.25. And then we divide both sides by 10.88. And these are pretty close to each other, so it's going to be close to 1, but less than 1 because your denominator's bigger. So a little bit under 1 second, that is when the t-shirts are they're headed for each other. And if you looked at the shadow that they project on the ground, that's when their horizontal locations are the same. Okay, so then the reason I'm making you do all this work, because it's pretty cool that now we want to see, they could be, because it's a two-dimensional problem, they could be in the same horizontal location, but in order to really collide in 3D space, you have to be in the same up and down location, right? So we're going to set y of Emma equal to y of Julian and see if we get the same time. Okay, so Emma started out on the cliff, 6.8, headed down at 3.26 t. You might have done this enough that you realize that 9.8 over 2 keeps turning into 4.9 over and over again. Julian had no vertical. He started on the ground, plus 4.7, but he was launching his t-shirt up, and gravity was also pulling him down at the same rate. So these terms go away, which is nice. It cleans things up a little bit. Okay, and then we're going to add 3.26 to both sides. Sorry, 3.26 t. And that gives us, these cancel, 6.8 remains on this side. That went away with that, equals 8t. Divide both sides by 8, and you get t is 0.85 seconds. Yay. So since they are in the same horizontal location when they collide and the same vertical location when they collide, they actually collide. So this is kind of proving the monkey hunter demo. Okay, so we know the time, but we don't know where they collide. So again, this is a review question. It doesn't matter which person we look at. So the horizontal location of Emma is 0 plus 4.43t. So that's 4.43 times 0.85, because that's meters per second times that many seconds, which is gonna give us meters. So again, I hope you figured out in physics. I want you to check your work. 3.77, that makes sense because let's see, she was only heading over at 4.43. So her horizontally, her bullet was doing, her t-shirt was doing this. His was going not twice as fast, but faster. So he's covering more ground per second. So they're going to collide closer to her than to him. Okay, so they horizontally are at 3.77, and vertically, she starts out at 6.8 meters above the ground, headed downward at 3.26 t minus 4.9 t squared. So now we can plug in the time. Minus 4.9 times 0.85 squared. I'm not sure I broke out what, oh, yes, I did. Nope, no, I didn't. So the height is not quite half a meter. Let's see if that makes sense. So pretty close to the ground. Half a meter is way less than this, but remember, this was launched downward and gravity's pulling them both down. So maybe I'll do this in, this is falling and this is falling. Oops, maybe more like this. And so they collide, at the two over and up, the X and Y values that we already found. But they collide pretty close to the ground based on our calculations. So that is the two-dimensional collision, where you need to know not just where they are horizontally, but where they are vertically. Okay, and then really good practice with speed. Calculate the speed of each bullet. So let's do Emma. And remember, it's a three-step process. Vx is just saying, hey, I remember Vx, it's constant. Let's just get it on paper down here so that we, have everything organized. Vy starts out with an initial speed, but is pulled downwards by gravity. But her t-shirt was launched downwards already. So her t-shirt is speeding up, right? Because her initial speed is negative and gravity is negative. So we're just going to get bigger and bigger negative numbers here. Minus 11.59. So we have, oops, that's meters per second. That's, her bullet is going over at that rate. And right when they collide, not when it hits the ground, but when they collide, it's going down at that rate. But the total speed is the Pythagorean theorem. 4.43 squared plus, technically negative, but when you square a negative, you get two negatives. So that becomes positive, and then you take the square root of that, and you get 12.4 meters per second. Okay, so again, check your work. The initial speed of Emma, even though we was 5.5 meters per second. And since it was speeding up, right, because gravity was going with gravity, y velocity was negative, gravity was negative, her impact speed better be less than be more than 5.5, because it's speeding up. And 12.4 is bigger than 5.5, right? And this doesn't have direction because this is speed. This has direction because it's a little bit over to the right and a little bit down, but the actual speed is always just how fast, doesn't have direction. Okay, so that's Emma, and let's do a different color. Let's see what's going on with Julian. And his initial velocity was negative 6.45. His initial y velocity, or his y velocity, it was headed up at 4.74, but gravity was pulling it down. So let's see what happened to that in 0.85 seconds. It has enough time has elapsed that his projectile has hit the peak and is headed back down, right? Because this is negative. So that's what's awesome about the math. We didn't have to calculate the time at the peak. We know it is beyond the peak because Vy is negative. All right, we are almost done. Now the speed of his is going to be the square root of 6.45 squared, and we can ignore the minus sign because we're going to square it, plus 3.59 squared. We can ignore the minus sign because we're going to square it. And I don't have what's under the, I just did all the math out, but it's 7.38 meters per second. So let's go back up and see if that makes sense. His initial speed was, let's uncover that, was 8. But remember, we figured out they collided pretty close to the ground. So if we found his speed when it hit the ground, it would have been 8. So it's less than the initial speed, right? Because his t-shirt's going to lose speed on the way up. At the peak, it's only going to be going 6.45, right? It never loses that speed. And then it's going to be going -8 when it lands, but the collision was, somewhere up here. So it hasn't quite regained all the speed that it lost on the way up. So that number looks good too. All right, so lots of good practice with review question of collisions.